Buenas tardes a todas y a todos los amigos de la Sociedad de Mecánica de Rocas de Chile. Hoy tenemos un nuevo seminario a cargo de la sociedad. El día de hoy tenemos la visita de Wilhelm Greuer de la empresa Stantec, que se encuentra en la ciudad de Michigan. Él obtuvo su doctorado en el año 2006 en Ingeniería de Minas, así como un magíster el año 99 en Ingeniería Civil y Medio Ambiente en la Universidad de Michigan. Tiene más de 13 años de experiencia en proyectos mayores. Su experiencia ha estado en minería subterránea y de superficie, como ingeniero de minas, planificación, operación, primariamente en base metals y otras áreas de la minería. Ha estado participando en diversos proyectos de distinta magnitud, tanto en el diseño, operación, monitoreo, y especializado en Crown Pillar y el uso de Backfill para el manejo de subsidencias. El día de hoy tenemos una presentación denominada Post-Pillar High Grade or Recovery, que nos va a presentar la experiencia de un proyecto aplicado que creemos que va a ser una contribución al conocimiento y a lo que hacemos como sociedad y que nos va a llevar a seguir discutiendo y valorizando lo que hacemos. So, Wilhelm, thank you very much again for your contribution to our society. We welcome you to this new seminar, and we are glad people is now connecting through YouTube and using Zoom as our main platform. So, Wilhelm, whenever you want.
Thank you for the introduction, and thank you for the opportunity to speak. And everyone in tonight's audience, thanks for tuning in. As per introduction, I'm Wilhelm Brewer. I'm a mining engineer who's been with Stantec for 3 years now, with the U.S. underground mining team, and I've been working in the industry prior to consulting for over 10 years for Freeport, Rio Tinto, Lundin Mining, and as a mine planner in the iron ore industry. And tonight's topic will be a case study of some work which we at Stantec did for a client recently, and involves the recovery of high-grade pillars from various mining panels where the post-pillar mining method had been employed. So the client is confidential, but the client company is a Mateer silver producer active in Latin America and listed on the Toronto Stock Exchange. And at the site, the post-pillar mining method is used in various panels, which currently presents 75% recovery, but the remaining pillars have very high silver grades. So any opportunity to recover those had been investigated, and the main pillar recovery challenges have been mining through and against backfill, because the backfill is of unknown quality and composition. That is, the batching of the backfill had not been tested rigorously, nor had there been records of backfill testing or backfill strength easily available. So basically, we're facing an unknown. Disclaimer, this is an engineering overview only. No financial information such as recovered tonnages and grades or costs and returns are disclosed, and as part of the original study, the sill pillar recovery is excluded. We're focusing on pillars within the excavation and not at boundary. The location is, as I mentioned previously, client confidential, so somewhere within these boundaries. And the client had been a client of Stantec's previously for several studies that I was involved with, including mining methods trade-offs and backfill engineering. And this had been the third study which I had performed for the client. The historic mining method at this site is the post-pillar method, which is, for those of us in the audience not familiar, overhand cut and fill plus a room and pillar hybrid. And the mining areas are bounded by sill and exterior pillars. The sill pillar barriers allow multiple areas and levels to be mined at the same time. So you're creating these autonomous panels. Post-pillar mining method is overhand in this site. The development consists of 6-meter drifts, or kais is how we pronounced it during the study, and then 6-meter crosscuts, or kamaras, as we had pronounced it during the study, leaving 6-meter by 6-meter pillars. And then the pillar support is for the back when progressively working our way up using overhand methods or top slicing, as well as the sill pillar. And then the backfill provides a working platform for top slicing, and it stabilizes the pillars or prevents them from unraveling due to higher concentrations of stress as the pillars develop in height. The pillar mining approach for recovery of the high-grade pillars included long hole methods, mechanical cutting through raisebore, and then cut and fill had been considered, but was ruled out early due to the fact that the costs became prohibitive, and that became apparent at a very early stage. So the study focused on the long hole and mechanical methods. The pillar access and challenges is mining new kamaras through pillars at the top level, mining through backfill, mining adjacent to backfill, leaving 24-meter sublevels, or with the vertical top cut dimension, that's going to be a 30-meter backfill exposure. So post-pillar mining and in-situ backfill. As I'd mentioned previously, the backfill quality is unknown. There are very few quality control records available. And the backfill placement in the historic or previous kais and kamaras is inconsistent fill, mostly unconsolidated rock fill or loose rock, and then end dumps which were covered with cemented rock fill and jammed, or paste fill was placed on top of the unconsolidated rock fill, and then jamming occurred using dozers. So prior to pursuing either option for this topic for recovering the pillars, we need to know what type of backfill we're up against. And so the site investigations consist of probe drilling, or going to the current mining level, the top level kai, and fan drilling, establishing drill stations between the remaining pillars, and then drilling holes to intercept the pillars and the backfill, and whatever core is recovered is logged for a RQD of the pillars and the backfill, as well as the contact zones between the remnant pillar and the historic backfill. Backfill strength is determined by selecting core for unconfined compressive strength testing of the paste, CRF, rock, any solid material at regular intervals, as well as examining and attempting to recover any core which would be compliant with testing specs from the backfill pillar contact zones. Paste fill at the site typically achieves a 28-day unconfined compressive strength of 250 kilopascals for samples cast at the paste plant. That is based on what records we could locate for testing of any of the backfill. And the in-situ unconfined compressive strength is typically, by virtue of rule of thumb and empirical data, 33% lower. So we're working with an assumed paste strength of or required backfill strength of 167 kilopascals. Remember that number. It's going to be discussed throughout the end of this presentation. Backfill strength requirements for single pillar mining, assuming adjacent cemented fill, that being paste or CRF. There is an arching effect, which is lateral stress due to backfill weight generating friction forces at the contact with adjacent backfill columns. And it's present at single phase exposures of a backfill column, say where you have backfill contacting the pillar on 3 sides and you have only one side exposed. And it's assumed where the exposure height, in our case we have 30 meters of exposure, is significantly greater than the exposure length, which is 6 meters, the lateral dimension of the pillar. So the arching effect, applying Mitchell's method to the 6 meter square pillars when the backfill UCS is 167 kilopascals at a factor of safety of 2, 13 vertical meters of pillar may be exposed. At a factor of safety of 1.5, the exposure height is virtually unlimited, and that just comes from Mitchell method calculations graphed to the right for your exposure height versus what your strength requirement is at your desired factor of safety. Now your backfill strength requirements for long, say 30 meter strike pillars. Typically, there's a diminishing arching effect where the ratio of exposed backfill height to strength is low, as we would see here. And the self-supporting backfill is subject more to vertical loading. There's less support on the sidewalls due to the arching effect, or let's say negligible frictional boundary support. With backfill UCS at 1,200 kilopascals at a factor of safety of 2, 30 vertical meters of pillar can be exposed at 1.5. The UCS is 900 kilopascal strength requirement for mining against a 30 meter vertical exposure. Summary of those strength calculations is mining 6 meter pillars is more realistic at 30 meter vertical exposure. Look at the second row. When you have a strike length of 30 meters, your strength requirements 900 to 1,200 kilopascals is significantly higher than doing a 6 meter strike length pillar. So you're looking at your cement requirements are typically going to run around 5% compared to backfill, which is suitable for mining the 6 meter pillars, that runs around 3%, maybe 4%. Cement is one of the major costs for backfill, and backfilling can be up to 20% of your total mining costs. So anything that is conserved in cement is a huge cost saver. Pillar mining methods. Doing the mechanical mining or conventional drill and blast. We're looking at either long hole methods or for the mechanized mining using raisebore. Now you see that we're mining against backfill of unknown quality and consistency in each case. So it may be necessary to develop a barrier between what is being mined from the pillar versus the backfill, or not keeping the backfill exposed. Access drift support to do development through and adjacent to backfill to get to the drill stations for mining. That will most likely consist of shotcrete arches or rigid steel reinforced shotcrete and spiling. These photographs are not from site. They are taken from a vendor catalog for shotcrete arches. For long hole pillar mining support, the risks and the hazards of long hole methods are going up against loose, weak, and inconsistent or unpredictable backfill quality. And the solution to that is a vertical spiling and grout barrier known as the pipe umbrella system. And the vertical spiling can be installed conventionally or through self-drilling methods. And these pipes support or reinforce a grout curtain. So a barrier is created between the backfill of unknown quality and stability and the actual remnant pillar, which can then be mined through long hole methods, as illustrated in the previous diagram. For raisebore mining stability, in that case, the remnant pillar is sized versus a reamer bit for the raisebore so that a shell, or as we pronounced it in the study, a scudo, is left behind in the pillar as a barrier against loose backfill. And this raise diameter is primarily determined by the raisebore rock quality. Raisebore rock quality is determined by logging core from the probe drilling, and it's used to determine what reamer bit thickness is needed to leave behind a scudo of a required thickness based on the rock quality and the level of risk tolerance. Raisebore rock quality is the product of the modified tunneling index of NGI multiplied by terms accounting for the shell or scudo stability and the jointing adjustment factor. So that's your Q sub R, which is plotted versus your desired risk tolerance or reliability to give you your raise diameter or your reamer bit sizing, so that you know how much of the pillar can you recover, what is the appropriate scudo thickness to leave behind, so that you have a stable barrier between mining activities and loose backfill. So overall for the study, we discussed mostly the geomechanical factors here, which came into consideration, although that was a part of other factors which had been considered in the trade-off. And I personally preferred the mechanized method, but where it had been where it had been at a disadvantage in comparison to long hole methods was for cost and productivity. It would have cost much more to do the raise boring rather than installing the pipe umbrella system. And then, you know, issues with mucking out the raise bore cuttings versus, you know, how long does that take versus, or how many times do you have to do that versus using the long hole methods. So taking everything into consideration for the pillar recovery in this trade-off, long hole methods were chosen rather than raise bore or cut and fill methods. So recommendations going forward, as we had included in the tech memo issued to the client: long hole mining method selection, blast 6-meter pillars individually, and then the other criteria from the past slide favor long hole mining overall, and probe drill before mining, so that we know what the strength and competence of the backfill is adjacent to pillars, as well as any potential escudo zone at the contact between the backfill and the remnant pillar. And core logging requirements are less objective for drill and blast than they are for the raisebore mining analysis. And then when using long hole methods, use the pipe umbrella system where needed, where you encounter loose backfill or anticipate loose backfill, or where you anticipate the backfill to be, in this case, less than 200 to 250 kilopascals in strength. All right, well, at this time, I believe we'll be taking any questions and comments. Otherwise, here's my contact information if you ever have any questions, or if you have any issues which you would like to discuss with myself or anyone on the Stantec team in the USA office. Thank you.
Thank you very much, Wilhelm, for your presentation. I think it's a really interesting topic. Now we're going to open the microphone for our members of our society to have questions, and also for people connecting on YouTube. I think I will begin. I took some notes, and just to talk about the risk in this kind of methods. I'm thinking you mentioned in your introduction the subsidence, and what are the risks associated with this method when you use them improperly, when you have let's say a blast that's not correct, or you're too close to surface, or you are using materials, or backfill doesn't have the properties you estimate. How can we manage, or what can we say about the risk in this method?
Yes, the greatest risk is the unknown. We don't know what the condition is of the backfill that we're up against, and so to mitigate that, the barrier systems are a preventive measure, and that's why, at this point, the mitigation is to get an idea of what type of conditions we're up against. There's the probe drilling, which is included in the recommendations, but even so, since we're at risk of losing the excavation due to a run of loose backfill, it's recommended that this is one reason why I preferred the raisebore method, because we're leaving a shell of remnant pillar in place of rock, a solid barrier to contain that backfill. Otherwise, using the long hole methods, there's the pipe umbrella system that creates a reinforced grout curtain, another barrier. So we may not know all of the conditions of the backfill that we're mining against, but by using these barrier systems, we will not see the backfill, so we're mitigating that risk. The consequences, of course, it could be, well, not only severely hazardous, but also the loss of each pillar that is being mined, because we have backfill running in and diluting blasted ore so that it's not economical, or the surrounding ground, the backfill, becomes so unstable that you can't place persons or equipment on top of it. So the real strategy here is trying to determine what quality backfill we're up against, and then creating barriers to keep it in place or contained.
Okay, great. I have another question related to the process of water. how could you manage, or how does the water influence the engineering of these methods? Thinking that you might be drilling, you might be blasting, you are working inside the mine, and you might have some problems related to unknown water. Does it change something when
Yeah,
you're applying?
we're not anticipating water in these historic mining areas. These areas had been drained previously, and these are panels within an active mine, so pumping and dewatering is ongoing.
Okay. And since you said that this area was drained, I don't think we have much experience of this method in Chile, and of course the use of backfill. I know in Australia, in the US, in Canada, the use of backfill is well known. Let's say we want to apply this in Chile. I know many students will be watching this video probably later and are now connected on YouTube. What can you mention a recommendation for the use of backfill? We know it in theory, we know what to mix, let's say cements and tailings, but we don't have much experience. So what can you, let's say, suggest to people that might be listening to this talk?
And the backfill type, that really depends on location. Some places which are more remote use cemented rock fill, so that mine development rock, instead of being stockpiled on the surface, can go back into the void. And otherwise, if a tailings storage area is close by, paste fill may be a better option, which is tailings mixed with cement to varying degree. And I know paste works well for long hole methods, but for cut and fill methods where the backfill is being jammed in place, cemented rock fill is more favorable. Overall, these methods are used for cut and fill, drift and fill, overhand, underhand varieties of cut and fill, and then drop fill for long hole methods. Any type of sloping operation.
Okay, great. I think we have a question from the public.
Sí, Matías, yo quisiera hacer una pregunta referente al grafiquito, a la tabla que mostró Will. ¿Dónde está incluido el factor tiempo respecto de las perforaciones, respecto a la forma mecanizada? ¿Cómo se evaluó? ¿Si está metido dentro de costo o no? Y la segunda pregunta es si se pudiera explicar un poco más a qué se refiere en el ítem Meaning Flexibility.
Okay, so we have two questions. The first related to the time effect. Let's say where is considered time in your evaluation in the table you show in your slides.
Yeah.
I think whether it's considered as part of cost or it's somewhere else inside the same metrics.
Oh, okay. For time, the cure strengths were 28-day strengths, but typically for backfill, what we see is usually like after 7 days, the backfill, at least cemented rock fill, but also certain types of paste fill, depending on cement dosages, they achieve about 75 to 90% of their ultimate or 28-day cure strength after 7 days or so. So using a practical approach at mine sites, I always allowed for a 7 to 10 day period of cure time for backfill prior to blasting within a certain proximity or mining adjacent to the backfill, because by 7 to 10 days, the backfill should have already achieved most of, as I said, 75 to 90% of its ultimate cure strength.
And in terms of the matrix, thinking in time, do you evaluate the time as another aspect, maybe in cost? That was maybe the question also from.
Yeah, it does factor in. That's why I'd mentioned previously, I usually just build in that 7 to 10 day period so that we could shorten the amount of time. I think at 70 to 90%, usually like the backfill has met its minimum strength requirements, so there's no need to allow it to cure to the full 28 days.
Okay, I understand. We have another question also from Yuri. He asked if you could explain further the term of mining flexibility. Mining flexibility you mentioned in your slide.
Oh, mining flexibility as one of the criteria for selection. Yes, that would be with using long hole methods, placing the drill on top of the remnant pillar. There, you can field fit your holes based on what conditions you encounter while drilling. Say all of a sudden you're, encountering rock or some void that shouldn't be there or anything, and you detect that in the drill cuttings, then you can adjust your drilling and your blasting plan accordingly. Whereas with the mechanized method, you just set up the raisebore and you pull the reamer bit up, and that's about all you can do. You have no options to field fit or change anything based on conditions that you're encountering as you're mining.
And that flexibility can be applied to other aspects of the process?
Yeah, for sure. I mean, while as you're drilling and you're encountering different conditions in the rock, then yeah, you can make any changes that are necessary. And I think this also goes for the sequence of pillars that you're extracting. I mean, moving a raisebore from one location to the next is huge versus moving stope drill. So if you do this with mechanized methods with the raisebore, most likely the raisebore is going to be moved sequentially from one pillar to the next. Whereas if you're using a stope drill, which can be moved more easily, then you can move that drill to the next whatever pillar based on what the upcoming grade requirements are.
And that flexibility, have you seen it's accepted in the mining companies? Thinking that sometimes we think we might look at the company as something more rigid, let's say, and this concept of flexibility also, it's a change in the way we think mining.
Yeah, I think that the flexibility that provides opportunities, which any mine operator, when they identify those opportunities, they're going to take advantage of them.
Yeah, it's an interesting topic to develop, since I think this flexibility can be applied to many areas and topics in geotechnical engineering, geomechanics, and mining.
Correct.
I think Yuri has one more. He asked what are the criteria to select the most relevant aspects in your table, in the metrics you showed. You use numbers like +1, -1, and 0. Do you think we can use some different way of
Yeah, I think there's room for improvement there, and that would have involved sitting down with the client and more thoroughly discussing what each criteria, what their priority is, so that we can add some weight to each criteria and come up with like a weighted scoring system versus just assigning 1 point per individual criteria. Come up with to determine what's their priorities, which criteria are more important, what's also for the health and safety aspect, add some weight to that so that it has greater influence or greater consideration than other criteria.
Yeah, sounds. We're used to see this kind of waiting in other areas, and sometimes we forget in mining. And in your experience, when you use this kind of approach, do you need to agree with the operator of the mining company? Is something you can suggest as a consultant, or is something that you need to discuss, agree? Because sometimes I guess I imagine looking from very far away. That you
Yeah,
have to, they ask you for your advice, but at the same time you are comparing different techniques, you have cost associates, and how is your
right.
maybe experience with that?
They're asking for advice, but we want to work with the client to come up with a solution which is, you know, delivers the best result, but is the most favorable for them to implement. We wouldn't want to expect the client to all of a sudden change everything that they're doing, because that could be a tremendous source of grief for them, and the result would be they would go to a different consultant who might tell them what they want to hear. But if there's any red flags, anything which we identify as a deal breaker, you know, anything which is a fatal flaw, that of course is something that we would have to discuss with the client, and ultimately, you know, what we put in our set of recommendations, what we believe is the safest and most acceptable way of achieving production. And you know, whether or not the client follows through, we have that in our set of deliverables, and but we try to work with the client to achieve the optimum results.
Good to hear your experience and how to work with clients. I think it's also something that when we share these talks to students, sometimes when we mention mining companies, clients, and the way of approaching to a solution might be also interesting for them to learn. I don't know if somebody else has questions. Si alguien más tiene alguna pregunta o consultas, creo que las he transmitido todas. En el caso que alguien tenga alguna pregunta adicional, por favor que la haga. I don't think we have any more questions. Wilhelm, thank you very much for your time, for your cooperation with our society. Also, we would like to thank Stantec for the opportunity to organize this. We are open to share the knowledge of rock mechanics in Chile and for the people connected on YouTube. Gracias a todos los que se conectaron, a los que van a ver este video y a los que lo están viendo. Creemos que es importante seguir fomentando la mecánica de rocas, discutir, comentar, conversar y seguir explorando lo que a todos tanto nos gusta. Thank you very much, Wilhelm, once again. Thank you very much to all, and have a good night.
Thank you.
Thank you.
Thank you, Will.
Thank you.
Thanks for the
Cheers.
opportunity to speak. Yep. Good night.
Thank you.
Bye.
Bye.
Chao.
Gracias, Matías.
Gracias, Yuri. Nos vemos, que estén muy bien.
Vale.
Adiós.